So good morning, everyone. I would like to welcome you all and thank you for participating in this webinar, which aims to explore the possibilities of signal processing in response to the future challenges and opportunities of advanced measurement systems. The webinar is motivated by the roadmap on signal processing for next generation measurement systems, which was recently published by the Measurement Science and Technology Journal of the Institute of Physics. It is worth noting that it is one of the most historical journals, almost 100 years old. To make this roadmap a reality, distinguished researchers from all over the world invested a lot of effort to identify impactful directions for future research. It covers signal processing considerations in contemporary measurement systems, optical measurements, biomedical measurements, remote sensing, environmental and industrial applications. I am the editor of this roadmap. I'm professor of signal processing and medical decision support systems at the Department of Computer Science and Biomedical Informatics of the University of Thessaly in Greece. And I'm also the director of the Biomedical Imaging Laboratory of this department. The speakers of this webinar are distinguished researchers, co-authors of the roadmap, who will cover a broad spectrum of topics ranging from basic to industrial research, organized in concise thematic sections that reflect the trends and impact of current and future developments per research field. Before proceeding to the webinar, I would like to introduce the speakers in the order of appearance. First is Andrew Yacoot, is editor-in-chief of Measurement Science and Technology. He leads the Dimensional Nanometrology work at National Physical Laboratory and chairs the BIPMs International Bureau of Weights and Measures, Consultative Committee for Lengths Working Group on Dimensional Nanometrology. Manus Henry is director of the Advanced Instrumentation Group at the Department of Engineering Science, University of Oxford, United Kingdom, and professor of load management at Coventry University, UK. His research interests include self-validating sensors and systems, particularly in flow measurement and enabled through signal processing. Today with us is Michele Nordia. He's replacing Silvano Donati, some connection problems. He's a professor in electronic measurements at Politecnico di Milano. His main research interests are optical and electronic measurements, interferometry, and instrumentation for industrial applications. Zhanghui Zheng is a professor and director of the Satellite Navigation Positioning Technology Research Center of Wuhan University in China. He is particularly interested in the challenges presented by multi-constellation and multi-frequency GNSS signal processing. I give the first presenter is Andrew Yacoot. Andrew.
Thank you very much, Dimitris. Good morning, everyone. Thank you, Dimitris, for the introduction. As he said, I'm the editor-in-chief and I work at the National Physical Laboratory. I've been editor since January and been on the board for about 15 years. And before we start the seminar and the detailed talks, I'd like to say just a little bit about the journal. So the journal, as Dimitris said, is coming up for its centenary. It was formed as Journal of Scientific Instruments back in 1923. This was a joint venture between the Institute of Physics and the National Physical Laboratory, the UK's National Metrology Lab, because it was recognised that measurement and instrumentation is fundamental to all areas of science and that really should be treated in many respects as a topic in its own right. Now, the journal was set up and has undergone several name changes, eventually being renamed Measurement Science and Technology in 1990. It's now on its 33rd issue. And as we said, coming up to its centenary, covering a broad range of measurement topics and instrumentation, which I think is really a strength of the journal. We have a very broad read, and that's illustrated by the broad readership. We have readers and contributors from university, industry, and the National Metrology Institutes. And the broad nature of instrumentation is very nicely represented by the these diagrams from the National Metrology Institutes that talk about the SI, the International System of Measurement, where we have 7 base units, all of which are defined or have a definition based on a fundamental constant. But and then from these units, we derive all other measurement units. But what becomes interesting is if you look at the 7 base units, there is an interdependence on them, in that for length, we can't have length measurement without measurement of time. And length measurement, the meter, supports mass measurement, the candela, and the Kelvin. So this is really showing how measurement is a very broad topic. There are common themes from many areas that have relevance for other areas. And signal processing is just one of them. Now, we have several recent topical reviews on a variety of themes that all have aspects of signal processing. And that was the reason why we decided to do a roadmap on signal processing. Also, we're planning some roadmaps for the future. So the next one is this roadmap on structural health monitoring. And as well as roadmaps, MST produces a series of special issues. So here is a selection of some of them that are coming up in the next few months. So I would encourage you to look at the journal's webpage, look at the scope, and consider contributing towards the journal, articles towards the journal. Now, without further ado, I think I will hand over to the next speaker, the first speaker, Manas Henry, who's talking about signal processing for contemporary measurement. Now, I hope you all enjoy the seminar and find it useful. Thank you very much.
Thank you very much, Andrew. Let me just share my screen. Start from the beginning. Okay, and I need to swap around, don't I? So I believe you can now all see my screen. Well, thank you very much, Dimitris and Andrew, for the introduction. I'm going to give the first talk in these series of sections, and I'm going to talk about signal processing for the challenges raised by the Internet of Things and measurements within the Internet of Things. So, we're all familiar with the concept of the Internet of Things, Industry 4.0, various other acronyms and ideas can be used, but the commonality is that they are set to revolutionize a wide range of industrial sectors, and this development places additional demands on the capabilities of sensors and measurement systems. So the traditional approach, I've worked in industry for with years, and the traditional centralized approach to control and measurement systems is being replaced now by a move towards self-organizing networks of components, and in particular, ubiquitous sensing. Sensing is everywhere, so more sensors are needed, but they need to be much more flexible in the way they operate and in the way they network and interface with each other, and the way data is fused at a higher level. Underneath all of this, therefore, there is a strong need for flexible, efficient in terms of power and bandwidth, and generic signal processing techniques to support this much more ambitious way of organizing data and sensors. Now, in our paper, we talk about 2 different approaches, and I'm going to mention one and then talk in more detail about the second, because that's my own research interests. So one example of how to provide a generic signal processing approach to dealing with signals is this recent IEEE recommended practice for signal treatment in smart transducers. And what the idea here is that we take some arbitrary signal and we analyze it and break it down in a standard way into a series of components, of shapes, where you can characterize the signal as a series of these shapes where particularly the parameters of that shape in terms of length and amplitude are measured. And this can be a standard way of conveying signal information to higher levels in a compact way so that high-level reasoning can be done. And this can be used in a generic fashion at any level. So that's one approach which I would recommend to be considered. And it demonstrates an attempt to solve this generic problem of how to do signal processing at all the different levels needed in the IoT. What I'm primarily going to talk about now is PRISM, which is a technique I and colleagues have been developing over the last 6 or 7 years. And this is a signal processing node with a standard design, which we'll see shortly. And it built into it is 1 or 2 FIR filters. So it's linear phase response, which is desirable, but it has a fully recursive calculation. So it's fast. And the computational cost is fixed no matter how long the length of the filter. I've used 100 million sample filters where it's only 50 flops to update the sample output. The design cost is also low, so you can create these things in real time in any IoT module or situation. And you build networks of these devices together in order to do useful tasks like filtering or measurement. So efficient use of compute power and flexible use for IoT signal processing. Okay. This is the structure of the filter, of the PRISM, and it consists of 6 or sometimes 4 Fourier-style integration blocks. And the way the mathematics works is you can just do these on a sliding window basis, but the outputs themselves are finite impulse response. If you have 2 outputs, they're orthogonal. And each one of these devices has a characteristic frequency, which is the period of the integration period. And it can have a harmonic number, which is the number of times the modulation sign is applied over the interval. And there's details in the literature. So what you get is a series of frequency responses, a whole family of these that vary with the input frequency and also vary with the parameters of the PRISM that you have. So what can you use these things for? Well, you can build trackers, which means that you can calculate frequency, phase, and amplitude of some input signal. You can build bandpass filters, low-pass filters, notch filters, which I won't talk about today, but also the latest and most exciting thing is you can do a very accurate version of FFT or DFT with windowing functions that arise from PRISM signal processing. So briefly look at these. So a tracker, what happens with a tracker is you can, you've got some signal coming in, maybe you do some pre-filtering. If you can use 2 prisms in parallel, the output of these prisms can be used to enable you to calculate frequency, phase, amplitude of the input signal. Simple piece of mathematics. So with these building blocks, you can track frequency, phase, or amplitude. You can also build bandpass filters. Again, standard design, so it's easy to instantiate one with whatever central frequency and bandwidth that you wish. A series of 6 prisms, simply selecting the parameters necessary to instantiate the filter that you're interested in, and then that could be followed up by a tracker in order to get frequency, phase, amplitude of the signal that you're interested in. So standard designs, throw them together, get the value that you want, get the measurement function that you want. You can also build low-pass filters, and this is starts to get more complicated. You have standard structures here now of series of prisms in series and in parallel, whereby using weights, calculated optimized weights, you can develop frequency responses that match your desired characteristic. And most interestingly, we can now build structures like this. So this is a 12-layer low-pass filter with minus 316 decibels attenuation, where the cutoff frequency can be anything you like. It's just a matter of how you instantiate this filter. And if you have a lot of prisms, that can have high computational costs. So I can convert that into a convolutional form. These 2 functions at the bottom are examples of convolutional forms of these types of filters. And this can actually be used now in the latest work that I'm doing to to be applied to FFT and DFT. And we can get ultra precise results for frequency phase amplitude emerging out of an FFT. And what I'll do now in the next series of slides is I'll show you how this can be used for frequency analysis with a particular simulated example. So here we go. So let's start here. So I'm sure everyone here is familiar with the fast Fourier transform and how good it is and how frustrating it is in some ways. So here's a working example. I've got 48,000 samples at 48 kilohertz, so 1 second of data, and I have 3 peaks that I want to chase. I've got 2 high peaks at about 1 volt, and in between them, I've got a small peak at 1 microvolt. And ideally, I'd like to be able to detect all 3 of these and get their characteristic, their frequency, amplitude, and phase, and so on. With a conventional, straightforward, plain FFT, what we get is this well-known phenomenon of frequency leakage. So you can see the 2 peaks, but this one is well and truly hidden. We can't possibly see it because the noise floor caused by frequency leakage is such that we can't see this peak at all. One well-known technique for improving FFT is to use what's called windowing functions such as the Han or Hanning window. And if you apply a Hanning window, you get much lower noise floor, and we can maybe just about see this peak. Better results on these 2, and maybe this peak just becomes visible. What we get now with a prism technique, where we use 2 windowing functions, and some of the filtering I was showing you before, we get this. So what we've got here is a noise floor at about 10 to the minus 12. And we have these strange constructions here. These are dead zones where we can't provide information. There's background mathematics behind this. But we can spot these 3 peaks clearly. And if we zoom into more detail, we can see what's really going on. So I'm zooming in now just to one of the peaks. And with this FFT, we're getting values at 1 Hertz intervals. All of the FFTs just give values at 1 Hertz interval values. The green stars here are from the conventional FFT, and around the peak itself, which is in the middle between these 2 boundaries, we're getting values of about 0.8 and about 0.7, nowhere near the actual peak 1.3, and that's pretty typical. I'm nearly done. The Hanning window gives slightly better results, but the prism result is right at the peak. And in fact, we need to zoom in to about 12 decimal places in order to start to see the difference between the true peak and the result given by the prism FFT. So it's extremely precise. Right, moving swiftly on. These are the statistics that we get on multiple values. So we've got, in this example, we've got standard deviations of e to minus 12, both frequency and amplitude, and also phase. So that's my big new exciting results that I hope to explain more about in the future. And just to conclude more generally, the Internet of Things offers new challenges and opportunities for signal processing. This prism signal processing technique provides a range of filtering and tracking techniques, which can be used both for real-time and indeed for offline or a discrete data set, such as spectral analysis. So we've got low computational cost, low design cost, flexible design. And so prism signal processing is an example of the type of signal processing that we need to support the future of flexible IoT systems. So thank you very much. I look forward to any questions.
Thank you very much, Manish. Any questions? I see no questions currently, so I would like to ask you a question. Where can we find more information about this prism FFT technique that you mentioned, Manish?
Thank you. Yes. In my presentation, I've cited some of the earlier papers on some of the earlier prism techniques. This new prism technique, the FFT technique, has been patents have been filed for this, but we're now going to move on to do publications. So I've given a link to an Oxford University website where a summary is provided, but over the coming few months, I hope to do both conference papers and also journal papers to explain this. And I'm also talking to potentially interested partners in this. I'm very keen to reach out beyond my own area of flow measurement to find other people who are interested in using this application, this technique, because I think it has very broad potential applications for spectral analysis. So please get in touch if you're interested. That's another answer.
Thank you very much. So I don't see any other questions. So maybe we should go on with the next presentation. It's Michele Nocia. Michele.
Okay, thank you. So now I think that I can share my screen and go in presentation mode. Okay, I hope that everyone can see the presentation now. Good morning to everyone. In this presentation, we talk about signal processing for interferometry, focusing on displacement measurement, because you know interferometry is a very wide subject. So I will start from very basic interferometric setup and historical signal processing for interferometer. Then I will focus also on a quite novel technique of interferometry, that is cell mixing interferometry, with dedicated signal processing for realizing, let me say, a new kind of instrument for different application. Going back to basic, as I told, we remember interference between waves is a well-known effect because electromagnetic wave is linear. So when you have the superposition of two waves, you can have more signal if you are in phase, or you can have a destructive superposition if you are not in phase. Taking advantage of this effect, 100 years ago, we had developed some structure, some setup of interferometer. An interferometer is an instrument that measures displacement, vibration, mechanical, dynamic properties of a target, taking advantage of this interference. In this slide, I'm showing the most used and also most famous kind of interferometer. It is the Mychason Interferometer that realized the interference between two electromagnetic fields, two beams of a laser source, using this beam splitter and two mirrors. What happens is the realization of a stationary wave. And in the stationary wave, we can measure the displacement of a mirror by looking at the amplitude measured by a simple photodiode. The signal given by the interference is a normal sinusoidal signal with this dependence on the target distance. What we have to process is this kind of signal. Going really back to basic, it's quite easy to understand that with a cosine signal, it's impossible to get the direction of movement because we have just the information of the cosine of the displacement. So historically, a couple of solutions were developed. One is the double beam interferometer. The other one is the double frequency interferometer. Double beam interferometer is realized by a laser that is in some way splitted in polarization. So we have two beams at two orthogonally polarized with two orthogonal polarization. And we add a little bit of shift on one polarization through a wave plate. In this way, we realize a sine and a cosine signal. Through these two kinds of signal, it's quite easy to recover the direction of displacement, as exactly as for an encoder. Maybe we all know the working principle of an encoder, and so we can simply count the fringes on the zero crossing in order to get the amount of displacement, and the direction is given by the first signal. If we have the sine or the cosine signal. So this is a very, very old kind of signal processes, but really robust. This kind of processing works. And you get something like lambda over 8 of resolution. Another possibility is to use two frequency. So to realize a laser source that generates two frequencies. The standard technique is to use the Zeeman effect in a helium laser. So this kind of effect realizes two frequency with orthogonally polarization and the frequency difference of about 5 megahertz. With the proper setup, you can measure the beating of these two frequencies with one photodiode for having the reference and another photodiode after the interferometer for having the phase shift. Now, signal processes require to measure the phase shift between two modulation at about 5 megahertz. There are techniques well known, as always, going back to the past, there is the possibility to have an analog processing with a simple mixing and the low pass filtering to get sine and cosine. Or maybe now it's easier to have an heterodyne down conversion and then sample the signal and make the phase measurement with digital algorithms that are well known. So these are standard interferometer that are used everywhere for displacement measurement. But today, I would like to focus on something that is more recent, that is a different kind of interferometry with the name of self-mixing interferometry. It's always a measurement of an interference, but the interference now is inside the laser cavity. This kind of interferometry measures a very small variation of the emitted power when a laser diode takes a reflection from a target, but a small reflection, not 100%. We are talking about 10 to the minus 6, 10 to the minus 5 in power. When we have a small back reflection inside the laser cavity, the laser cavity shows a modulation. This modulation is linear for very low back injection. Here you can see the standard cosine signal, depending on the distance of the target. But when the back injection increases, we get a distortion up to a strong distortion and also hysteresis. It indicates that the signal keeps the information on the direction of the target movement. Because you see this distortion is no more linear with respect to the phase. On this kind of signal, you can see in literature hundreds of papers showing different techniques for taking the information on displacement. Now I would like to summarize on some techniques that are quite easy to explain in a few minutes. First technique is quite easy. Let's count the fringe. Every fringe, as old interferometer, shows a movement, a displacement of the target of half of the wavelength. But for this kind of interferometer, you can also recover the direction because, for example, you can measure the duty cycle of each fringes. With a duty cycle higher than 50%, you're going in one direction, lower, you're going in the opposite direction. But this kind of reconstruction system is always limited to a spatial resolution equal to alpha wavelength, and also the in case of strong signal fading due to speckle effect, it's impossible to recover the displacement. Another technique really used for application, I also know a company that realized instruments based on this kind of technique, is the phase unwrap, because when the back injection becomes stronger, the signal shows this kind of subtle light behavior that is almost linear inside the fringe. Then you have a jump with always the same period of λ/2. It's quite easy to implement a signal processing that is just an unwrap of this kind of signal. So when you see the jump with a nonlinear filter, you remove it and you can reconstruct the signal in this way. This is a real measurement. The signal of the self-mixing interferometer can be reconstructed in real time simply by this kind of unwrap. As you can see, the spatial resolution is improved. We go now down to some tens of nanometer, limited by the non-linearity of the system, because the fringes are not really linear, you can see here, but also limited by the signal-to-noise ratio of the signal. Another strong limit for this kind of signal processing is the requirement of having a strong back reflection. If the signal back reflected by the target is not high enough, you cannot proceed with this kind of system. In order to overcome this problem, another possibility for signal processing for this kind of interferometer is in the frequency domain. Because if you take a small windows and then elaborate a fast Fourier transform, interpolated, or what you prefer as algorithm for getting the frequency of the main tone, you can have a direct measurement of the speed, because this is a simple Doppler effect. But there is something more. If you look also at the second harmonics, you can also get an information on the direction. And so by applying this kind of algorithm, you can reconstruct in real time the displacement also for a signal that shows a strong degradation from speckle pattern. This is an example when we have a real-time signal processing in order to get the reconstructed displacement. We also realized a real-time system based on FPGA, and I can show here some real measurement. This is a signal with strong signal fading from a speckle effect. You see the fringes that goes down, but the reconstruction is really good. And also another example of reconstruction, there is a comparison with a commercial triangulator, but placed at 15 centimeters, not at 5 meters of distance. So I would like to conclude, because my time is expired, with the conclusion on what are future challenges. I go back to my real world and application. I think that the future challenges for interferometry and signal processing for interferometry is to try to reduce cost and size for having more possibility of application to different solution in industrial or biomedical or what we want, where now interferometry is not used due to the cost. So signal processing will go on this direction in order to find solution at lower cost and size. There are other challenges, for example, getting the best sensitivity for something like gravitational wave detection. But I think that signal processing will be really useful for reducing cost and size. So I thank you for your attention, and I'm open for questions.
Thank you very much, Michele. I don't see any questions in the question answer box. So please if anybody has questions, do add one in the question and answers.
Yes, yeah, now say, okay, there is a question. Can you say anything about the non-linearity of the interferometer? Okay, now if I have understood, sorry, there are also, what? Oh, sorry, there are two possibilities of questions. Let's see, there are, what is a measurement rate or current generation of cell mixed interferometer? Okay, so non-linearity of the interferometer depends on what we are talking about. If we talk about self-mixing interferometry and possibility of linearized fringes, it depends on the particular situation, on the laser itself, because every kind of laser show a different behavior. Talking about the order of magnitude, I can say that number of papers shows non-linearity in the order of some tens of nanometer in the reconstruction. If we are talking about the non-linearity in standard interferometry, normally we should be limited by resolution, not by non-linearity, because it depends on the algorithm that you use for reconstruct. If you go back from the cosine signal, you use a reverse function, you can go down to some few, let me say, picometer in some kind of realization, but it's a completely different application because you use typically high power laser with high cost system. I don't know if if the question was about this, because standard interferometry doesn't have a intrinsic nonlinearity. Then, sorry, going back to the other question, what is the measurement rate of the current generation of cell mixing interferometry? It depends. But because if you consider application like the commercial one made by Philips, realized with an ASIC, it goes with very, very high frequency. We are talking about the sensor used in the mouse, optical mouse for high performance, and they go at million of measurements per second with a very high frequency modulation. If you talk about vibrometer, what I see is typically application up to some hundreds of kilohertz, because cell mixing is still a sort of poor interferometry. It's not, let me say, it's interferometry for low cost application due to its very easy setup and to the problem that the signal due to the back injected reflection is quite low. So with respect to a standard interferometry, the signal to noise ratio is not as good. So normally cell mixing interferometer doesn't work at very high frequency. I hope to be clear, and I think that I'm at the end of the time dedicated for this section.
Thank you very much for answering the questions and for the presentation. Okay,
thank you. And now
for the next presentation, it's my turn. So I will share my slides. So my presentation is about optical image processing for in vivo measurements and diagnostics. It's part of the biomedical measurement section of the roadmap. We focus on non or minimal invasive optical imaging techniques. Optical imaging is a non-invasive and non-ionizing technology which uses light to probe cellular and molecular function in living subjects. Endoscopy is a basic tool for in vivo optical imaging that can be complemented by merging techniques revealing tissue properties valuable for diagnostic purposes. For example, multi or hyperspectral imaging, optical coherence tomography, near-infrared fluorescence imaging. It is generally applied for the visual examination of various tissue structures, and it comes in different flavors. For example, we have laparoscopy, we have gastrointestinal endoscopy, arthroscopy, and many other endoscopic processes. The most challenging one is the endoscopy of the gastrointestinal tract, mainly because of the length of the gastrointestinal tract, which reaches 9 meters. There are ways to reach the gastrointestinal tract from the upper side, where you can use a gastroscope, or from the lower gastrointestinal tract using a colonoscope. However, the limitation is that they cannot reach the small intestine. For this purpose, capsule endoscopes, like the ones we show here, have been introduced, and since the beginning of 2000, they are used for the examination mainly of the small intestine. In the next years, the capsule endoscopes have been evolved, and currently there are also capsule endoscopes for colonoscopy. These are colon capsules with 2 cameras like the one you see here. The advantage of the flexible endoscopes compared to capsule endoscopes are that they have tools, they can carry tools to perform dissections of polyps and perform treatment generally. Also, they can spray water to clean up the regions and have a better view. The challenges with regards to in vivo optical endoscopy measurements include the measurement of the size of objects of interest, of the depth, the travel distance of the capsule endoscopes, and also optical biomarker assessment to assess whether there are malignant lesions or other types of lesions inside the gastrointestinal tract. In flexible endoscopes, it is very common to use reference objects, for example, the size of the forceps, but this is a really rough measurement that can be done with this way. A recent technique that requires special hardware is structured light. We can see it here where a grid is projected on the tissue, and this can be used to assess depth and size for the particular measurements. Capsule endoscopes are more challenging. There's no reference that can be used. They are usually monocular. Currently, they are monocular, but of course, there are currently some research attempts where we have also stereo capsule endoscopes. Their localization is quite difficult because it is sensor-based currently, based on triangulation of RF signals. And SL, structured light, could be also an alternative. However, it has not been yet applied. Currently, experimental state-of-the-art solutions include the exploitation of image features like lightness or color or other image features to implicitly predict depth, mainly based on artificial neural networks. Here is an example of an architecture that we have recently proposed. It uses 2 images, 2 subsequent images, to estimate the disposition of the displacement of the camera during the different axes, hip Z. And this is based on features, extracted image features like the coordinates, intensity, and color of the images. And this way, we are able to measure the size and the distance traveled of the endoscope. The size measurements that have been done show that we have 0.19 millimeters of accuracy error, for 0.95 millimeter targets. Depth assessment today is performed also using deep learning. This is deep artificial neural network architectures used for depth estimations, with most of them having taking as input real images along with depth maps. Depth maps are images where the actual depths of the different objects appear with different gray levels. So after training, they are able to automatically extract features that can infer depth. However, a challenge is that within the gastrointestinal tract or in any other endoscopic modality, it is difficult to obtain ground truth in vivo. To this end, transfer learning techniques have been applied using pre-trained on benchmark datasets that are not non-endoscopic, and these and the RMS error on these were approximately 3.9%. To cope with low accuracy of deep learning techniques in vivo, we have combined both deep learning and geometric approaches to estimate the size and the depth of objects of interest within the gastrointestinal tract. And this has been done considering a virtual grid that is generated based on the intrinsic parameters of the camera. I cannot say more because the time is very limited, but you can see all the references that we have in our roadmap. And by successive application of depth measurements, we can measure the travel distance of the capsule endoscope or any other endoscope. Currently, with regards to these kinds of measurements, we are in two early phases where we have used phantom models like the one you see here to measure distances, travel distances. For this is 30 centimeter, and the error we managed using intelligent techniques was 1.21 centimeters. There are also optical biomarkers assessing the type of lesions that can be found within the gastrointestinal tract. There have been several methodologies assessing the color, texture, and shape features. Very interesting results can be obtained with multi and hyperspectral imaging, where biomarkers revealing tissue characteristics that would otherwise be invisible to the human eye appear. And state-of-the-art approaches on this direction include deep neural networks. However, they require large annotated datasets of images, and the reported accuracy range have a big range because it depends on the problem, on the data set, on the types of lesions, etc. Current and future challenges include the validation of the performed measurements, which is difficult to establish a ground truth measurements in vivo. Also, another challenge is to consider the elasticity, deformability, and motility of the living tissues. A big problem is that the data are limited due to the vague and inflexible ethical legal data sharing frameworks. The need for image annotation by medical experts is important, and it's very difficult to obtain annotations because they need time to be obtained, and also they are costly. DNN models, that is deep neural network models, are black box models that are not explainable. Clinicians cannot understand the reasons for the inference of a machine learning system, and this makes them hesitant in adopting these such technologies in clinical practice. There are limited efforts to this direction. The accuracy of image-based in vivo measurements depends on image quality as well. This is due to image resolution limited by camera miniaturization and energy requirements, artifacts by the image communication channels, lossy image compression algorithms, for example, for bandwidth and storage. And there are many artifacts due to the body fluids and other contents, for example, mucus or debris. To obtain another challenge is to obtain coherent, consistent results on different images acquired from the same or different systems. For example, to obtain comparable measurements from consecutive endoscopic video frames, or obtain comparable measurements of the same target using different endoscopes. And also challenges appear by application of application on the techniques that we have investigated in the gastrointestinal endoscopy domain to other endoscopic imaging modalities. Advances in science and technology to meet the challenges include novel ex vivo or in vivo experimental setups that can be developed. Also, very challenging is the in vivo, the in silico modeling and simulation that we can achieve today with the computational power that we have. We can develop multi-physics models. We're using finite elements, considering the material properties as well as the motility of the living tissues. So we can do more realistic experiments, and also we can exploit rendering. As you can see here, the images are very realistic. This is a rendered model. And deep learning can be used to enhance the efficiency of FEM simulations, and also for the generation of images. These here are artificially generated images that we have made using a generative adversarial network that can be used for training of the deep neural networks. Other advances include the novel deep learning techniques with fewer data requirements. We need to minimize the requirement for annotations. So weakly supervised, one-class classification, semi-supervised techniques are suggested, as well as several image quality enhancement approaches. Concludingly, current advances on image processing and analysis indicate the feasibility of accurate image-based contactless in vivo measurements for minimally or even non-invasive optical imaging systems. The translation of most of the current research to clinical practice requires efforts mainly towards enhancing their robustness in a data-efficient way, testing their performance in environments that enable a closer approximation of the real world in vivo conditions. And we hope that addressing the challenges identified in this presentation will contribute to the evolution of the next generation in vivo optical measurement systems that will be safer and less discomforting for the patient, and efficient for the medical professional and trustworthy for them. More about this can be found in our article, and more about biomedical measurements you can find in section 4 of our roadmap. I'm open for questions. I don't see any questions. Yeah, I see. Thank you very much for this question. I see a question about how fast is this in vivo technique. The answer is that it is very fast. Regarding, It depends on which of the in vivo techniques you are addressing to. I assume that you are addressing in the size and depth measurement technique that I described, which was based on a single image. This technique is very, very fast. It's less than a second. It requires less than a second to estimate the size of or the depth of a lesion. Okay, thank you very much. So there are no other questions. I will proceed with presenting the next speaker. The next speaker is Yankui Zheng.
Okay, yes.
Thank you.
And you can see my desktop?
Yeah, we can see your desktop.
Okay, good. Okay, hello everyone. So this is the best greetings from Wuhan University in China. So I'm going to talk about the global navigation satellite system, which is the short name of it is Gnss. And I'm going to talk about some future design of the augmentation, Gnss augmentation that is based on real constellations. So there is no question for, oh, sorry, this is the second page, some problem for it. Okay, so there is no question for the Gnss, for the role of Gnss, which is the key national information infrastructure, and it has been everywhere for our lives. And at the moment, we have 4 global constellations, which is from the GPS, GLONASS. Both were developed in the 1980s, and the latter 2 were the BDS developed by China and the Galileo system developed by the European Union. And the BDS system has been established, has been fully operational since the year of 2020, and the Galileo constellation is still under construction, but it can provide some preliminary positioning functions. All of these constellations will have about 30 satellites to provide global coverage and to achieve instantaneous positioning for any users on Earth. And for the orbital altitude of each satellite is about 20,000 kilometers. So you can see how far these satellites are away from us. And we have 2 other regional navigation satellite systems, that is QZSS developed by Japan and the NAVIC system developed by India, which are based on some geosynchronous satellites to provide a constellation focusing in Japan and India respectively. All right, so no matter what kind of constellation we're going to have, the basic function of Gnss is to provide instantaneous initialization to achieve about 10-meter positioning precision at any place and any time when observing enough satellites. So you have to, whenever you are in the outdoor environment, you can observe at least 4 satellites, and then use the trilateration technique, you can achieve a 10-meter position precision without any latency. That means at the first epoch of the data processing, you can achieve a 10-meter positioning precision. We call this the instantaneous initialization. So what's the problem? The problem is 10-meter positioning precision is not enough for some kind of applications like the precision agriculture, where you needed to spread the seeds using the tractors precisely and with the precision of about centimeter to decimeter level. And there is no such critical requirement on the initialization efficiency. You can always have the precision to be achieved within 5 minutes. But for the disaster relief, like the earthquake and the tsunami early warning system, and you have to determine the ground motions caused by the radiated waves, radiated seismic waves within seconds. That's we call it the near instantaneous. So we have to achieve about centimeter to even millimeter level positioning accuracy within this environment. And for autonomous driving, which is a very hot topic today, and you have the centimeter level and the decimeter level positioning to be achieved, but you need to have this kind of positioning accuracy within one epoch. So that means to achieve instant or instantaneous positioning accuracy, you don't need to wait, or you can't wait before you can have this kind of high accuracy position to be provided for drivers. How can we achieve the high precision GNSS? The basic method is to provide augmentation to the current GNSS constellations. So we have to build a global network of base stations with the interstation distance to be from 1,000 kilometers to even a few tens of kilometers. So using these augmentation networks, we can derive very more precise orbits and clock areas for the satellites. And then, because we refer our positions to these satellite orbits and clocks, and then we can have a very precise position to be computed. But before that, we have to also to interpolate the atmosphere refractions for the electromagnetic waves disseminated by the satellites. So here, if you have a very dense network, you can derive a very precise interpolation of the atmosphere refraction. But if you have a very sparse network, augmentation network, the ionospheric delay and the tropospheric delay cannot be computed very precisely. Now we have a number of GNSS augmentation systems, such as the QZSS CLAS services and the Galileo HAS and the BDS PPP B2B services. And they are free systems, I think, and but you have to wait for about 10 to 20 minutes before you can achieve a centimeter level positioning, because they don't provide a dense augmentation network. But for the following commercial networks, such as Trimble RTX, Fugro G4, and the Netcom Starfire, they have a very dense network to be provided for some regions, for some specific regions. So we can achieve a centimeter level positioning accuracy within a minute, and that can facilitate a lot of applications. So then what's the problem with the current existing GNSS augmentation? The first one is, if you want to achieve high precision positioning accuracies, you have to build a very dense ground-based network with interstation distance below 50 kilometers. But this is unsuitable for global high precision applications, because you can't have all of these base network to be built on oceans or in deserts. The second one, if you don't have such kind of augmentation network, you have to tolerate a very long initialization time of about over 15 minutes. And this is not good for some time critical applications like autonomous driving and geohazard monitoring. So what we are going to propose here, and what is being done in China, is to build a mega constellation satellite constellation, which is composed of LEO satellites, the low Earth orbiters, with an altitude of about smaller than 1,000 kilometers. So in this case, we can have global coverage for instantaneous high precision precisions within about 10 centimeters. Because of the low orbital altitudes, the satellite geometry changes very quickly with respect to the users on Earth. So we can have a very fast convergence of our position accuracy within a few epochs to the centimeter and millimeter level. So this is the basic idea. And the problems to be resolved is the first one is the constellation design, because for each pass of the LEO satellite, the time can only be about 20 minutes, and you have to ensure you can have the ground station to receive the signals from these high dynamic satellites. And the second one is to integrate the time-space datum of the GNSS satellites and the LEO satellites. The third one is to redesign the navigational messages for the LEO satellites, because their orbital characteristics is totally different from that of GNSS satellites. The final one is the combination model, the data processing model to integrate the GNSS data processing and the LEO satellite data processing for the highest precision and the highest instantaneity. So we use some semi-physical simulations system for the LEO augmentation testing And here we are using a Gnss plus Leo positioning receivers to receive the signal from a simulator. And then, so you can see here the results from the left graphs. We see if you use only BDS constellation, I mean the Gnss constellations, and you have to wait for about 10 minutes before you can achieve a centimeter level positioning. But after you have the Leo constellation, about 100 satellites to be included in your data processing, and you can achieve the positioning precision of about 1 centimeter within 30 seconds. So this is on average. So we have tested a lot of stations, and we can see here the average from the right figures. We can see the average initialization time for the Leo augmented positioning is about 1 minute, and you can achieve such kind of centimeter level positioning precisions very fast. And now, And now in China, we have begun to build the CentiSpace constellation composed of about 115 Leo satellites and 4 master stations. And these satellites will orbit around the Earth and at an altitude about 1,000 kilometers. That will improve the position precision and the reliability of BeiDou positioning. And we built a communication link between the Leo satellites to transmit the data collected on board of the Leo satellites in real time. And that can facilitate the orbit and the clock determination of the Leo satellite constellation. So here we can achieve a very fast real-time positioning efficiency, including both the position precision and fast initialization. I'm sorry. Okay, this is the top left figure shows one of the master station built within China to monitor the health conditions of the Leo satellites. And the following one is a cartoon of the Leo satellites, which have been launched into the space. And now we have just a few of them to be about 10 satellites to be launched into the space. And afterwards, we can have more than 100 satellites to be launched into the space to form a constellation. And now the signals of the noise of the Leo pseudo-range signals is similar to those of the BeiDou of the BDS constellations. So they have very comparable positioning quality. And we can see the orbital precision for the Leo satellites is very similar to that of the Gnss satellites. And we can achieve a 3D orbital precision of about 2 centimeters, which is enough for us to determine a precise position of centimeter to millimeter level on the ground, receiving both signals from BeiDou constellation and CentiSpace Leo constellations. So my final page is about the shortcoming of the existing high precision Gnss augmentation, because whenever you want a very high precision positions, you have to build a dense space network and to achieve that kind of precision instantly. But once you don't have this kind of dense network, you have to tolerate a long initialization before achieving high precision precisions, and that long initialization can last for about 10 to 20 minutes. And if we have the Leo augmentation for about 150 Leo satellites for global coverage, and we can have fast geometry change which can lead to faster positioning initialization. So you can have the positioning high precision positions within about 1 minute. And we have the inter-satellite link between the Leo satellites for data transmission in real time for the ground data processing to produce the highly precise orbit and clocks for the Leo satellites. And the application of Leo augmentation is that we can use this kind of system to augment the autonomous driving, where we have to have the precise position instantly for drivers to prevent any kind of collision of the vehicles or any instant match of the maps and the positions of the vehicles. Okay, that's all I have. So you're welcome to have any questions here.
Thank you very much, Zhanghui. Are there any questions for Zhanghui? We're approaching the end of this webinar. So I don't see any questions. Thank you very, very much for this excellent presentation, Zhang.
Okay, you're welcome.
And I think that we are at the end of this webinar. I would like to thank all the speakers and all the attendees for participating in this webinar. I hope you found it interesting and useful, and that you will find our roadmap also very useful in our research. Have a nice day.